In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of one...
All right, gentlemen, we are live.
Excellent. Thank you, everyone, for being here and tuning in for Reading and Research Night. I'll throw the standard disclaimer out there that I always do on these nights that we don't really put... Oh, I have an echo. 1 second. I apologize. Classic mistake. Okay. Sorry about that. To my stream. In any case, standard disclaimer, we don't really put together presentations for Reading and Research Night. We don't do a bunch of planning. We don't, it's really just about literally reading, literally watching videos sometimes. Tonight, we will be watching videos. And so if you want to come chat with us, watch videos with us, and talk about, specifically tonight, we're going to talk a little bit about Heisenberg uncertainty. We're going to talk a bit about Schrodinger's cat. So if you want to come watch videos and chat about that stuff with us, you can come join us on Discord. Head over to ethercosmology.com. Click on the little Discord icon, and you can join us that way. And without further ado, anything else we should preface with here, Alan?
No. So tonight we're going to kick it off with the history of the vector potential. So Bennett and Pizio have been going back and forth with the vector potential. So we're going to learn a little bit about that tonight. We got a video queued up for that. And then after that, we're going to watch a mainstream physics channel talk about his understanding of the uncertainty principle in Heisenberg and Schrodinger's cat. And then we're going to watch It's BS give his interpretation of quantum mechanics regarding the Heisenberg principle and Schrodinger's cat. So each video is about 15 to 20 minutes, and there'll be commentary in between, I'm sure. So let's go ahead and start it whenever you lads are ready.
Thomson and Stokes were perhaps the most important.
Yeah, cool.
In a letter...
Ooh, I just had to do the little audio thing real quick, but yeah, it's streaming now, and we're good to go. You know when you lads are in?
I'm here.
Yeah, for sure.
All right, let's go.
Sorry, I couldn't come to Israel to give this talk. My topic is history of the vector potential. Most of the content of my talk have already appeared in this article by Alfred Wu and myself. The vector potential was introduced by many people in various contexts. Of these, Thomson and Stokes were perhaps the most important. In a letter dated in 1850, Thomson wrote to Stokes, "My dear Stokes, do you know that, etc., etc., that, etc., etc., is what is now called the Stokes law or Stokes theorem. We all know that that is the foundation of differential geometry. Maxwell wrote 3 papers. The second paper was published in 5 installments. Commonly, it is thought that paper 3 is the most important. People usually call that the origin of Maxwell's equations. Actually, Maxwell's 2 key ideas were in the first 2 papers. In the third paper, he only put the 2 together and created the name of field theory. If we look into Maxwell's first key idea in paper 1, it was the idea about how to understand Faraday's electrotonic state. The electrotonic state, was a vague idea which Faraday had believed in, but was unable to clearly define because Faraday did not know very much of mathematics. In 1881, years after Faraday and Maxwell were both gone, Helmholtz had this to say: Faraday found that an electromotive force striving to produce these currents arises wherever and whenever magnetic force is generated or destroyed. He concluded, that means Faraday concluded, that in a part of space traversed by magnetic force, there ought to exist a peculiar state of tension, and that every change of this tension produces electromotive force. This unknown hypothetical state he called provisionally the electrotonic state, and he was occupied for years and years in finding out what this electrotonic state was. In 1856, Maxwell found the answer to this puzzle, and that was that the electrotonic state was the vector potential. In modern notation, we would write E equal to minus A dot. He published this in paper 1. He was 26 years old. That he knew he had landed on something important, and that it might lead to disputes about credit. He was very well aware of. So at the end of the paper, he had this paragraph: with respect to the history of the present theory, that means electrotonic state is equal to A, I may state that the recognition of certain mathematical functions as expressing the electrotonic state of Faraday and the use of them in determining electromagnetic potentials and electromotive forces is, as far as I am aware, originally. This is, in my opinion, a completely fair statement. But the distinct conception of the possibility of the mathematical expressions arose in my mind from the perusal of Professor W. Thomson's papers. You see that here Maxwell was very careful. He did borrow from Thomson the idea of the vector potential. So he was afraid that Thomson might take offense. That's why he made the statement. But in Thomson's papers, although there were extensive uses of the vector potential, Thomson never linked that with Faraday's ideas of the electrotonic state. So the credit should go to Maxwell 100%. Thus, to Maxwell, A is central to his understanding of electromagnetism. That is probably why in all his later papers and in his books, he never eliminated the vector potential. But now, before we go on, let me mention a puzzle. Maxwell knew that the vector potential was not uniquely defined. So we should ask, which choice of A, in modern language, which gauge did he select to be the electrotonic state? in writing this, in formulating this formula at the bottom. If you want to search through that paper, one of his, this is the paragraph which has some bearing on this puzzle. Maxwell wrote, "We have now obtained in the functions alpha 0, beta 0, gamma 0, that means the components of vector potential, the means of avoiding the consideration of the quantity of magnetic induction which passes through the circuit. Instead of this artificial method, we have the natural one of considering the current with reference to quantities existing in the same space with the current itself. To these, I give the name of electrotonic functions or components of the electrotonic intensity." The emphasis in red were Maxwell's original one. This is the only paragraph in which perhaps Maxwell was really referring to the different gauges. This paragraph seems to suggest that he chose a gauge where A is inside of the electric wires. If so, does there exist such a gauge? Does there exist such a unique gauge? All of these questions Maxwell never mentioned. And this remains perhaps an important subject for the historians of science to look into. Be that as it may, it is clear that the vector potential being identical to Faraday's idea of the electrotonic state was Maxwell's great first discovery in his paper 1. Then in his second paper, the key idea was the displacement current. This has been well discussed in recent literature. This is again a very puzzling development, because as I said earlier, paper 2 was published in 5 installments called part 1, then part 2, then part 3, then part 4. And it was only in the 4th installment, part 3, where the displacement current occurred. In earlier parts of this paper, you find the diagrams, intricate diagrams like this, with vortex motion. These are very intricate. What was clear was Maxwell was struggling to find a mechanical model to explain the vector potential in the electrotonic state. Then suddenly, in the 4th installment, we find the following paragraph. Proposition 14. To correct equation 9 of part 1 of electric currents for the effect due to the elasticity of the medium. This correction was the addition of the displacement current. So puzzle, another second puzzle. How did Maxwell arrive at this correction? This is a question that I've studied for some time and did not know, did not explain. Maxwell evidently, in the first 3 installments, struggled to make a mechanical model that he thought would, in some sense, be the analog of electromagnetism. In the process of this, perhaps when he tried to study the question of charge conservation, I don't know, maybe when he landed on the idea of trying to explore the question of charge conservation, when he realized that he needed to add an additional term, This, in my opinion, is another great puzzle in the history of physics. After Maxwell's death in 1879, Heaviside and Hertz independently presented Maxwell's equations with A eliminated. Heaviside especially was extremely happy with this elimination. He said in 1889, the psi and A are murdered. Psi is the scalar potential. The psi and A are murdered, so to speak, with a great gain in definiteness and conciseness. In 1892, he said, the duplex method being the method using E and H without A, the duplex method eminently suited for displaying Maxwell's theory and brings to light many useful relations which were formerly hidden from view by the intervention of the vector potential and its parasites, the parasite being the scalar potential. Of course, we all know that indeed it is true. After we eliminate the vector potential, the equations look more symmetrical with respect to a dual transformation exchanging E and H. And that evidently was one of the reasons that greatly delighted Heaviside. So after Heaviside and Hertz, there existed a dogma. The dogma says electromagnetism resides in E and H. Where E and H are zero, there's no electromagnetism. This became a dogma, and in the first 60 years of the 20th century, this was what every student of physics was trained in. When I was a student in China, and later a graduate student in Chicago, this was the thing that we all learned. Then came 1959, the great paper of Aronov and Bohm, the paper that we are gathered here today to celebrate. Their proposed experiment was finally done by Tanamura et al. Quantitatively. That experiment was a decisive one which shattered the age-old dogma and revealed the true importance of the vector potential. And that is that in quantum mechanics, E and H under-describe electromagnetism. Only knowing E and H is not enough. Even when E and H are both zero, there is still possible electromagnetic effect. On the other hand, if you take the loop integral of the vector potential over all loops, that over-describes electromagnetism. In other words, you do not need that much of information to realize all the electromagnetic effects. It is this expression which, over all closed loops, that correctly describe electromagnetism. Thank you.
Hell yeah.
Love that drive-by at the end. Just flash you the big equation. There it is. Boom, bang. Okay, great. That's what we're waiting to see. Bye. Not
Yeah,
gonna
that
a
really
damn
caught me
thing
off guard,
about
man.
it. I feel so jilted.
Me too, man.
Feel
It
robbed.
felt like he
That guy
really-
dragged me through every word on his slides, and then he goes, "Oh, yeah, that's great. Okay, thank you.
Right.
I'm
Like,
gonna
so much
kill that
stuff, like,
asshole."
boom, there you go. Bye.
Oh man, my bad, boys. I only watched like 2 minutes of it before I was like, "Oh, I'll save this for tonight." I didn't know he was gonna
I
rob
mean,
us.
granted, it was a good setup. Like, it was
Great history lesson, right?
some pretty good history
Wow.
in there. Yeah.
You know what it reminded me of? I don't know if you've ever talked to Cyrus, but he studied a lot of Steinmetz and Heaviside, and that removing of the scalar potential and the vector potential was huge in terms of hiding the ether in modern days, right? And that displacement current thing has got a lot associated with it. If you remember back on the Anel Denew paper, where he's saying that there was never any experimental evidence of that, because basically what they're saying is that as the electric field, as there's a change in the electric field, like when it like loses energy or whatever, it just spontaneously creates a magnetic field, and then when that magnetic field changes, it creates an electric field, just like self-inducing, with no charge potential accelerating in between them at that intersection point.
The old charge potential just kind of manifesting from nothing,
Yeah, and then
or transmitting across nothing, rather.
yeah, from nothing, and then it became something that is nothing. You know, like all right, cool. But yeah, we'll definitely come back to Anel Denew and vector potentials. So if did anyone have anything else they wanted to add or questions on that video?
None here.
All right, we'll move on to our boy Floathead Physics. I actually like this guy's channel. He's pretty good if you want to get some mainstream info or whatever, some clarification. He's usually a pretty good speaker. So we'll go ahead and check out his thoughts. He says here he misunderstood Heisenberg's uncertainty principle until now. So we'll see what he forgot.
Thank you, Brilliant, for sponsoring this.
Hopefully he didn't find the answer in a TV guide article.
Well, spoiler alert. Have you seen this one?
Video. This is the Heisenberg's uncertainty principle, at least a version of it. Not only does it make the atom stable, but it allows you and me to exist. But wait a second, what exactly does it say? Well, here's how my teacher explained it to me. If you look at this photo taken by a high-speed camera of a moving tennis ball, you know exactly its location. But do you know where it's going? I'm like, no, it's a photo. So it could be going in any direction. I have no idea, meaning I have no clue about its velocity. But what if I took a long exposure photo of that same tennis ball? Ooh, now I know it's going in this direction. And by looking at the blur, I can estimate its speed as well, which means now I have a much better estimate of the velocity. But notice, now I don't know where the location of the ball. I don't know where the ball is, so I've lost the location information of that ball. In other words, if the uncertainty in finding the location of an object is very tiny, then the uncertainty in finding the momentum of the object, because the momentum is given by its velocity, that is very large. But if you know the velocity or the momentum very nicely, its uncertainty is very small, then there will be huge uncertainty in the position of the ball. And guess what? Elementary particles like electrons behave in a similar way. If you find its position exactly, you wouldn't know where it's going. You wouldn't know anything about its momentum. On the other hand, if you find its momentum exactly, you wouldn't know anything about its position. If you take the uncertainty in the position and the momentum, together they must have a minimum value. And that minimum value happens to be h divided by 4 pi, which is the uncertainty principle. Now, for a long time, I thought that this makes so much sense, like so much intuitive sense. But then I realized there's a problem with the analogy. You see, if you go back to that photo, I can actually figure out the velocity of the ball over here. You know how? Instead of using a still camera, I use a high-speed video camera. And then I just look at the next frame, and by looking at the next frame, I will know which direction the ball is going, and I can figure out this distance and calculate the velocity. Higher the frame rate, better my calculation. So this is just a technological limitation. I can figure out the velocity, but Heisenberg's uncertainty principle, it is not a technological limitation. Another explanation I heard was that, hey, if you try to figure out where the electron is, you have to bounce off light on it. And when you do that, you're going to disturb the electron, disturbing its momentum. And that's why you will have no idea about its momentum when you learn about its position. But again, the problem is the uncertainty principle has nothing to do with measurement. It is much more subtle. So for a long time, I thought I would never get a rigorous intuition behind what's really going on over there. That is until I read Feynman lectures, and then my mind was truly blown. So the hope of this video, if I do it right, is not just to understand the principle, but to actually rediscover it intuitively so that we'll understand it in our bones and guts and it'll make perfect sense. And I think Feynman helped me do that, so I'm sharing it with you. So if you're ready for this, let's begin. So where do we start? Feynman says we need to first understand the idea of wave-particle duality. And I'm like, wait a second, I know what that means, right? I mean, electrons, for example, are both waves and particles at the same time, right? And Feynman says, no, not quite. I mean, what do you mean? Well, Feynman asks, Mahesh, if you have an animal that flies like a pigeon, but also has a face like that of a mouse and the fur that of a mouse, would we say that animal is both a pigeon and a mouse at the same time? No. No, it's not. It's a different
I would
animal
ask him which way to
altogether. It
Narnia.
just shares some common properties with these two, but it's a different animal altogether, right? Similarly, an electron has certain properties that are similar to that of the traditional particles. For example, they come in lumps, he says. So you will always find an electron in one particular location. You can count 1 electron, 2 electron, 3 electron. They're not spread out or anything like that, okay? Which is very similar to how particles are. They come in lumps, like the grains of sand or a tennis ball or other things like that.
Kind of like step back and like right now, like come in lumps, particles. It's just like you can really, if you can step out of your way you've been brought up, just kind of look at it from an outsider perspective. Like this is pretty bizarre kind of religious stuff.
I see it as a screening process for the gullible.
Yeah.
Yet at the same time, a tiering process for those, intellectually capable to actually understand the abstract concepts at the same time.
Yes.
You have to have both of those qualities.
And I don't mean that as like a personal dig at him, but just in general, like this stuff is so insane sometimes, the assertions that get made, that get layered upon assumptions, it's just
They just skirt
crazy.
right over them, yeah.
Yeah. But yeah, you're right. It also is impressive to be able to, go layers deep on the abstraction like that. But yeah.
But the electrons are not particles. Why? Because they do certain things that normal particles don't do. For example, if you were to set up an experiment with the 2 holes, which is the double slit experiment, and shoot electrons through them, you will get something which you wouldn't expect from grains of sand or tennis ball. You'll get a pattern that
See, this is where it's about to get crazy, dude. We're like particle, particle, particle. Only ever wave.
looks like
Something
this.
that just can't be
Think about
found.
How does that make any sense? Normal particles don't do that. Therefore,
Yeah, we got to end on that video.
Definitely,
electrons
yeah.
are not
Hell
normal
yeah.
particles. But this pattern is an interference pattern that you get from waves. And therefore, this means electrons also have properties like they interfere, they diffract. Properties that we associate
Are they
with traditional
beachfront properties?
waves.
Oh, dude, check this out. He's about to set you up for the ultimate beachfront. Check it out.
But does that mean they're waves? No, because remember, waves do not come in lumps. They are continuous. They are at multiple locations at the same time. But electrons come in lumps.
No lumps
Which
of
means
waves.
they're neither
Roger.
waves nor particles. They're their own things. Feynman says they act screwy in their own way, which sounds disappointing, right? But here's the good news. Electrons are screwy just like how protons, neutrons, or even photons and other things are. They're all screwy in the same way. So the physics for them is pretty much the same. We call them quantum objects. So they are neither particles nor waves. They share certain properties with particles or waves, but they're neither of them. This is the whole idea behind the wave-particle duality. Okay, so since Heisenberg's uncertainty principle applies to quantum objects, our next question would be, how do we deal with the momentum and the position of quantum objects? So let's start with the momentum.
Oh, I think we missed it, but when he was given his electron explanation for why there's only the interference pattern, he goes, well, we know that it's that the electron's interfering with itself in a superposition. It's like, dude, what?
So it's like you could order your burger meal both with and without fries at the same time, but you're gonna know about it till you open the bag, right?
No biggie.
Feynman asks,
Sneak
Mahesh,
that
do you
in.
want just a formula to calculate momentum of such quantum objects?
Yeah, then, dude, where did he go into? I could have sworn 'cause this is where I stopped, but he talks about the which way. He takes it to the which way experiment, which is like another layer of abstraction to the double slit.
Give him 20 seconds, see what happens.
Yeah, maybe we'll get back to it.
Objects, or do you want some intuition behind it? I'm like, of course, give me the intuition, right? So for that, Feynman says, let's go back in time a little bit, around 1900s, where we thought we understood what light was. We celebrated, thinking that light is an electromagnetic wave. We understand optics is solved, almost all the physics is solved, nothing else remains to do. Only to realize a little bit later that there were certain experiments like the photoelectric effect or the black body radiation, where we couldn't explain what was going on using the wave theory. This is where folks like Max Planck and Albert Einstein came along, and they realized that light must be coming in chunks as well, must be coming in lumps as well. The quantum nature of light was discovered by these folks because of these experiments. This is your photons. And the energy of the photons, they hypothesized, has to be given by this particular equation. E is equal to h nu, where E is the energy of the photon, h is the Planck's constant, and nu represents the frequency of light. Well, earlier it was just a hypothesis, but then experiments like photoelectric effect actually confirmed that this must be true. Okay. Now, at this point, Feynman asks, Mahesh, do you see something interesting over here? And I'm like, no, this is a usual equation. I know about it. What would I see? Feynman says, if you were de Broglie, okay, or de Broglie, however you want to call him, okay, then you would notice that, hey, nu is the frequency, right? Frequency of any wave is given as c divided by lambda. And I'm like, yeah, so what? Well, now if you bring the c on the other side, you get E divided by c on the left-hand side. And I'm like, yeah, so what? Well, from the classical electromagnetic wave theory, the momentum of an electromagnetic wave is given by E equals C. Sorry, E divided by C. Do you remember this, Mahesh? I'm like, yeah, I kind of remember this. We did a video on it, a video where we showed why light has momentum even without mass. We showed that the light's momentum comes from its energy. I don't have to watch that video. I'm not.
Got that massless momentum?
Fishing for views, but
they just kind of showed it to you, did they?
It intuitively over there,
Okay,
so you can
go ahead,
check it
go
out if you need to do that. But this comes from classical physics, okay? But anyways, de Broglie, what he says, what he looks at it and says that, hey, that means I now understand that the momentum of these quantum light particles, whatever you want to call them, that should equal the Planck's constant divided by the wavelength. I have an expression that connects the momentum and the wavelength. Why he got excited was because he said, look, if light, which we thought was a wave, happens to have particle properties, maybe particles like electrons, which we thought to be particles, may also have wave properties and might also have wavelength associated with it. So maybe this equation also works for electrons. That was the hypothesis that de Broglie put forward. Again, back then it was a hypothesis, but today we have verified it, that this is true. So this works not only for photons, but all quantum objects. And that means if you want to find the momentum of any of these, like say electrons, this is how you find it. You take the Planck's constant and divide by the wavelength, and that's how you calculate the momentum of the object. At this point, Feynman is like, Mahesh, you could have put in some simulations over here to get the point across better, right? And I'm like, yeah, I could have, but I don't need to, because you can find those simulations at brilliant.org, the sponsor of this video. I love Brilliant. And of course, you will also get a 20% off on the annual premium subscription if you decide to buy it. The link is also in the description. All right, Heisenberg is waiting for us. So this is how we think about momentum for quantum objects. But now comes the last question. How do we think about position for the quantum objects? That's the last piece of the puzzle. And for that, Feynman says, again, we have to go back in time a little bit, okay? Once we put forward this hypothesis that these electrons, for example, can have wavelength, a question was asked. If electrons have wavelength, they should also have a wave equation, right? Where's the wave equation? And that's where Erwin Schrodinger says, hold my cat. He comes back in a year with the wave equation, which we call today the Schrodinger's wave equation. This equation looks scary, and maybe it's a topic for a future video, but what's important is that it encapsulates all the properties of these quantum objects. Actually, not all. Some properties like spin was not captured very well. Anyways, then comes the big question, what does that equation even mean? I mean, think about it. If you solve this wave equation and you get a wave, say, that looks like this for an electron, what does that wave represent, right? Because it's not the electrons are wiggling up and down. No.
That's not a
this
wave,
itself
that's a
is
pulse.
the electron. Then what do these peaks and valleys even mean? That was the big question. Well, we call these peaks and valleys, the symbol that we use to represent the peaks and valleys is psi. And we realize that maybe psi doesn't, the peaks and the valleys don't really mean anything. But we also realize that if you take a square of these peaks and valleys, then that gives you the probability of finding the quantum object at that particular location.
The square of
Wait,
what? Their length or their amplitude? What the fuck?
One real quick thing that must be pointed out is they get this little wave right there, right? And they calculate it with their math, but it's also a measurement, right? Like that right there, if they had a detector and they hit it with energy, they say they hit it with an electron or whatever, that's the energy it would register when, I guess 2 electrons hit it or whatever. Well, that would mean that the energy is spread out over the entire length of the wave. But they're like, no. There's 1 electron right here, and it's here.
That's just the detector ringing, not actual matter ringing.
Yeah, it's like, where is the energy at, right? Is the energy located at one point in time? Because the electron is a point particle, meaning as soon as it touches it, it's only in contact for 1 instant. So how is the energy being transferred over a period of time that's finite? It's just a wave. But anyways.
No, thank you. Like, as he was saying, he doesn't even believe in it. But if you square it, that's where it lives.
What does that mean? What do you mean, Feynman? Okay, Feynman says, Mahesh, look at these locations. Okay, what's the value of psi over here? The amplitude, it's 0. This means the probability of finding the electrons over here is 0. So if you were to shine light on this electron to try and locate it, there's no chance that you would find the electrons in these locations. On the other hand, look at these locations. The psi value is very high. So the probability of finding the electron over there is very high. So if you were to shine light on this electron, there's a very good chance you'll find the electrons over here. And this is the coolest, weirdest thing about quantum objects. They don't really have a position until you measure it. It's not like you don't know where the position is. No. We know that the position can be anywhere here and here. It's inherently probabilistic. It has nothing to do with our measuring tools. They don't have a position until you measure it. Okay, so if you put it all together, we now understand how to think about momentum of such quantum objects, and we now understand how to think about position of such quantum objects as well. And now let's put these two together to build the uncertainty principles ourselves. So Feynman, what do we do next? Feynman asks, Mahesh, can you imagine an electron which has a specific value of momentum? And I'm like, yeah, if it has a specific value of momentum, it's moving at a constant velocity. I'm imagining it like this. And Feynman is like, no, Mahesh, you're still thinking classically. See, these are quantum objects, right? So if they have a specific value of momentum, they should have a specific value for wavelength. So a better way to imagine this is a wave of a specific wavelength, and this wave would extend all the way to infinity. And I'm like, wait a second. I get that electrons have wavelengths, so we are drawing a wave, but why does it extend to infinity? Why can't I represent it this way? Well, because look, the wavelength here and the wavelength here is different, right? The wavelength over here is infinity actually. But we said that this electron should have one value of wavelength everywhere, which means the electron should look somewhat like this. It should extend all the way to infinity everywhere in the universe. So now think about its momentum. Okay, so since I know its momentum perfectly because it has one specific value of momentum, delta P is 0. There is no uncertainty in momentum. But what about its position? Where will you find this electron if you were to measure it? Well, for that, the probability, it depends on the amplitude square, but look, now the amplitude is the same everywhere, which means the probability of finding this electron is the same anywhere in the universe. In other words, the uncertainty in finding this electron is infinity because I can find it anywhere in the universe. This is the key that Feynman says. Yes, this is nonsensical, but if you try to create a quantum object which has one value of momentum so that there is no uncertainty, look, you inevitably end up with having infinite uncertainty in its position. Not because you don't know its position. No. Now, the probability of finding that electron is the same anywhere. That's why the uncertainty goes haywire and becomes infinity, right? Now, let's try to think about a more realistic quantum object. So we need to localize it a little bit more. I need to narrow down its position, which means I have to decrease its uncertainty. How do I do that? Well, again, think about it. If I have to narrow it down, I have to make sure the waves have zero amplitude at some places. How do you do that? Well, Feynman says just add more waves to it with slightly different
Mathematical band-aid.
Why? What does that do?
All right, so what we're going to do here, boys,
because
is
it
set
has
up
slightly
a
different
S-matrix
wavelength, there are
series,
certain
do a
locations where the
little
waves of the peaks and the
perturbation theory.
valleys will line up over here. In these places, the amplitude will be much higher. But there will be also other places where the peaks and the valleys line up like this. In such cases, they will destroy each other. Destructive interference. And when we do that, we'll now end up with a new wave that kind of sort of looks like this. I know it looks ugly, but look what we have done. Because now there are places where the amplitude is very high and other places where the amplitude is low, I have narrowed it down. So this is much better than before when it comes to position, but it comes at a cost. You see, because to narrow down the position, I had to add two waves of two different wavelengths. That means now this object has two values for momentum. What does that mean? That means if you are to now measure this particular electron's momentum, there's a 50% chance of having it to be either one of them.
You cut your certainty in
other
half.
words, narrowing down the position, decreasing the uncertainty in the position automatically has now increased the uncertainty in momentum. It's no longer zero. You can see right in front of your eyes, it has nothing to do with measurement. That's how the quantum objects work. And if you want to narrow it down even further when it comes to position, you add even more waves. You can do that. But if you add more waves, you're going to increase the uncertainty in the momentum even further. Decreasing one increases the other. Beautiful, isn't it? And by the way, I know these are ugly drawings.
Oh
So
my
here's
God,
an
I wanna
Audacity
throw
simulation
up in
over
my
here.
mouth, dude.
If I add two waves of slightly different wavelength, look, I can
I mean, in a twisted
I can
way, it's
destructively
beautiful.
interfere them so that I can narrow down the positions. High probability of finding the electrons here.
It's
But
not
if I
about
add
the
even
measuring,
more
it's just the way
waves,
they
see, I'm
look.
narrowing
So
it down
beautiful.
even further. In the limiting case, I can add so many waves of different wavelengths such that I will get one specific location where there's a high amplitude and almost zero amplitude everywhere else. Now, this is a highly localized electron. The probability of finding the electron is super high in this region. That means the uncertainty has gone down dramatically. But because I've added so many waves of different wavelength, it has so many values of momenta, that means its uncertainty in the momentum has gone up. So this is it. This is the uncertainty principle. Nothing to do with the measurement, nothing to do with our instruments, but inherently how quantum objects work. Just think about this. Try to create a quantum object in your head which has a perfect value for momentum and a perfect value for position. It's not possible. Okay. And
Yeah,
that's
real
the
quick.
uncertainty principle.
He's actually correct on one thing. It's not about measurement. This is just how they work. But the reason why that's how they work is they tried to narrow down a wave into a point. See, if it's just a wave and its energy exists across the entire length of those little wobbles, which is how a wave works, then it's not a point at all and you can't quantize it as such.
So you're
Man.
telling me that the belief that their waves are made of discontinuous discrete packets of quantized energy is what's ruining and holding them back?
Yeah, I'm saying that if it was actually a point, you wouldn't see a wave. You would see a flat line, and then there'd just be a giant spike in it, and then another flat line.
Hmm.
That's what a point would do. Not a continuous wave function where the energy is varying across time. But you say that it's like it just it doesn't actually appear anywhere until we measure it. That's
Yeah.
I want to
be-
give them all like wedgies and like take my fist and like rub it across their head really hard and stuff them in a locker.
Nice.
So that's why if you take their product, it should have a minimum value, Heisenberg said, and that minimum value happens to be h divided by 4 pi. We can derive this as well intuitively, which we'll probably do in a separate video, but at least we got the essence of it, right? Finally, Feynman, how does the uncertainty principle stabilize the atom? Well, if you go back to the classical model of the atom where the electron is going around the proton, say in the hydrogen atom, then this cannot work because the electrons are charged particles. So charged particles, when they accelerate, they should lose energy to radiation, which means as it loses energy, it should plummet into the proton. But that doesn't happen. Why? Nobody had a real answer for this. But Heisenberg's uncertainty principle can help us understand why that cannot happen. Well, the simple answer is electrons are not simple particles.
How's that song go? The mass cancels out. What is it?
Particles, they are quantum objects. So think about it this way. The uncertainty in the position of the electron is pretty much the size of the atom, right? If the atom is so big, we know the electron has to be somewhere over here and not somewhere over here. So there's a high chance of finding the electron over here. So its uncertainty is over here. Now, if the electron were to plummet towards the nucleus, towards the proton, then its uncertainty would reduce. And if the uncertainty in the position becomes very small, its uncertainty in the momentum would become very large, meaning the electron would now have much larger velocity, which could actually propel it outwards. And that's why, because of that undefined very large momentum, it will not be able to it will not actually fall into the nucleus, it will come right back up. So the uncertainty principle ensures electrons do not lose energy and fall into the nucleus. It's the principle because of which electron has to be having some energy and stay away from the nucleus, and that's the reason why today we think of it in terms of an electron cloud. The uncertainty principle saves the atom, it stabilizes the atom and allows everything to exist, including you and me. So what do you think about this? Do you think you now have a much
Thank God
better
for that
intuition?
math right there.
Man, that was.
I feel like
long.
every. I
If
feel
we
like
didn't have
every
that
single-
math, we wouldn't be here.
I feel like every single one of these people need to do some research on what epistemology is, because they have none.
Nope, they're just playing the game and playing it well. That's how you can string together a video like that.
The electron doesn't actually exist anywhere. It exists everywhere until you measure it, and then it exists somewhere. I mean, how does that sound like it's coherent to them when they say it? How do you say that with a straight face?
You can't. You have to do the feigned excitement. Everything he said was like a laughing joke throughout the video. I don't know if I've just never noticed it. The couple of videos I've watched of his, or if this was like just particularly egregious in this video, but everything was like a laughing inside joke thing that wasn't funny.
Well, his sponsors are very happy that he's so enthusiastic.
Yes.
I mean, that's just one of the. I feel like that's just one of the results of being in that world for so long. It's like, yep, it doesn't make sense, and you're stupid if you think it should.
Crazy,
Just,
dude.
you know, sarcastically laugh at yourself about everything, because that's what life is. It's just a big
Fox.
joke. 'Cause
Cat video. You guys want to suffer
Well, it's
through
like they're
one
playing a
more?
giant game of like theoretical make believe, and that's fine. Like, if we were to pretend that this
Maybe
is
the
how
first
it works,
option
this is
is
what it would look
all
like. And then they just take a giant leap and they're like, oh, by the way, it's not a game of pretend, though. Like, we are going to actually treat this as if it's real because we think it's real. Like, how did we make the logical leap from this game of pretend, where you go into a world in which there's no definite deterministic reality, and then say that, well, if it was like that, this is what it would look like. And since we're able to make up math for it, then it just must be real, actually, in reality anyway. It's that logical leap. Like, how do you not realize you're making that logical leap that's completely incoherent?
Because you're not getting censored on YouTube, and it feels good.
Think you get
It
paid
is
enough
called
money not to?
mathematics.
Paying the rent.
It, it is called mathemagics, and it is giving him very good livelihood. Okay.
Okay.
All right. Well, we can suffer through one more, or we could hit our boy up. It's up to you guys.
Let's hit our boy up.
Thank God. All right.
Yeah.
So we'll start with quantum entanglement, right? And then we'll get into the old finding the electron here. All right. Take it away. It's BS. All right. I got you, bro.
This is the 4-page paper that describes the extremely overhyped idea of quantum entanglement. It was written in 1935 by authors Einstein, Podolsky, and Rosen, and is commonly referred to as the EPR paradox. The purpose of this EPR paper was to use the math of Schrodinger's wave equation and disprove Heisenberg's uncertainty principle. The uncertainty principle is one of the core foundational papers of quantum mechanics, and Heisenberg tries to convince you that the world is inherently indeterministic. In other words, it is impossible to accurately predict what is going on in the world of atoms. We will come back to Heisenberg's paper later, but now let's look at a visual representation of what the EPR paper is describing. Schrodinger's equation describes how wave systems move. For example, you can think of this as a wave on the surface of a lake. Now forget that idea because quantum mechanics hijacked Schrodinger's equation. They want you to think of this as a wave of math, or specifically a wave of probability. So now we take the idea of electron particles and force them into a wave equation. And these waves each have their own wave equation associated to them. Now we take this two-particle system and continue to evolve it over time. At this point, the two particles begin to interact and create what is known as a quantum state superposition. So going back to the EPR paper, we have a two-particle system that came together and interacted in the quantum state superposition, and now we will move this system forward in time so there's no longer any interaction between the two parts. So let's evolve this forward in time, and now we have the two parts separated again. So that's the basic logic behind the setup for this bug. We started with two separate equations, and then when they interacted, and this is the key, we can then combine those two separate equations into a single equation. This is where the bug begins because we now have a single equation that represents two separate particles. So then after the interaction, the combined system can then be calculated. So this is the system after the interaction, and here is how you exploit the bug. You measure only one of the particles in this two-particle system. Now, because you've measured only one particle, but this entire system is represented by a single equation, that means that this particle must collapse into a determined state. So the measurement of that single particle caused the entire wave equation to collapse. Now remember that one of the two particles was never directly measured or directly disturbed, and this becomes very important when it comes to disproving the Heisenberg uncertainty principle. Then the EPR paper goes on and describes, using math, what we now would consider quantum entanglement. And they finish the section by relating it directly to the Heisenberg uncertainty principle. What this is saying is that you can take a measurement from the first system and then use that information to plug it into the entanglement math. Then that will tell you what the second system is doing, without in any way disturbing or measuring the second system. Okay, so at this point, who cares? The EPR paper says all of this stuff, but what does it really mean? This was a direct attack on quantum mechanics and what we now call the Copenhagen interpretation. Paul Dirac was one of the main contributors to the Copenhagen interpretation. He was a skilled mathematician, and 2 years prior to the EPR paper, he had won a Nobel Prize for his work in quantum mechanics. Let's look at how Dirac responded to the EPR paper with this Niels Bohr interview that occurred 1 day before he passed away. So the interviewer commented that this paradox provoked a great stir among physicists. Dirac said several times, "Now we have to start all over again because Einstein has proved that it does not work." He also mentions that Heisenberg tried to write something to refute Einstein, but he made an error and therefore had to give it up. And he says it again and calls Heisenberg's attempt nonsense. And remember that Heisenberg wrote the uncertainty principle paper that is being directly invalidated by the EPR paper. And again, the question was asked, did Dirac think he had to give up quantum mechanics? Then Bohr replied, yes, at that time, but they had to convince him otherwise. So the EPR paper meant serious business. You had two of the mathematicians that founded quantum mechanics, and neither one could refute the EPR paper. At this point, the popular science stories will generally send you down the path of the great Bohr and Einstein debates. But the EPR bug is telling us that there's a problem with the uncertainty principle. Another name that Heisenberg wanted to use for this paper was the principle of indeterminism. In this paper, Heisenberg is trying to convince us that the quantum world cannot be determined by this type of continuous line, and you have to look at it as discrete points. But why is this? Heisenberg justifies this by discussing the problems of using a light photon to measure an electron. So at the instant when you try to measure the exact position, the electron undergoes a discontinuous change in momentum. So the more precisely you determine the position, the less precisely the momentum is known. In other words, if you know the exact position, you cannot know the momentum, and that is the indeterminism. So back to the EPR paper, they are measuring the first particle, and that allows them to predict with certainty, using the entanglement math, the values of the second particle. So that's the killer. You know the values of the second particle without disturbing it. So EPR is a workaround for Heisenberg's requirement that you disturb the system when you measure it. Let's look closer at how Heisenberg came up with that idea. He is using a gamma-ray microscope to determine the position with as much accuracy as you want. The idea is that the gamma-ray photon smashes into the electron, and that is what causes a discontinuous momentum in the electron, or that's what disturbs the electron. The next sentence is the exact bug for this paper, saying that the change in momentum is greater with smaller wavelengths of light means that he is using the 1 second photon energy per wavelength flaw. He is using Einstein's photon flaw to justify the indeterminism, or the discontinuous changes in the path of the electron. So this is where he uses Einstein's idea of high energy photons and his own idea of indeterminism. He is trying to figure out the orbit or the path of an electron in a hydrogen atom. You shoot a single gamma ray photon at the electron and that ejects it completely out of the hydrogen atom. So the path of an electron has absolutely no meaning, and it cannot be determined. So you can see here that Heisenberg's uncertainty is based on the idea of Einstein's high-energy photon flaw. This summarizes the problem with Heisenberg's uncertainty principle paper. If you don't understand the issue with this equation and what I'm calling the Einstein photon flaw, then you can take a look at these two videos on my channel that will help describe the issue to you. This one is the short version, and this one is the longer and more detailed version. So this is what the EPR paper is really trying to tell you. And as you can see, it is a really crushing bug report. And to quickly review, the quantum state superposition is what creates the ability to measure a single particle and collapse a pair of particles in the same wave function. The entanglement math allows us to invalidate the Heisenberg uncertainty principle. And then in his paper, we see the high energy photon idea that is supposed to create indeterminism. But since it doesn't do that, then that leaves us with the Born rule. This is where Max Born started the idea of indeterminism and probability and quantum mechanics. Max Born hijacked Schrodinger's wave mechanics equation, then attached his own meaning of probability and indeterminism to that equation. It was that idea that created quantum state superposition, which is not real. So the EPR paper exposed all of these issues and completely shuts down quantum mechanics. And finally, quantum mechanics is a pseudoscience based upon forcing the idea of material particles into equations that describe waves through a medium. And thanks for listening.
Well
If anyone wants to write that definition down, right?
So he's saying that physically speaking, the reason that Heisenberg thought that there was this uncertainty to begin with is because the act of measuring, it's not that the act of measuring collapses the wave function, it's that what you're using to perform the measurement is a gamma ray, and when you smack an electron with the gamma ray, it sends the electron flying.
Yes, sir.
Well, no wonder you can't continue to measure it after that. What?
Hey, no, it's just indeterministic, bro. Can't. It's just the way it is. It's quantum weird.
It's like saying, that's like saying, hey, if I am throwing a beach ball through the air, I can track its path, but as soon as I try to measure it, well, it's like taking a giant baseball bat and smacking it. Well, after I smack it with the baseball bat, it doesn't hit the ground anymore, like I thought it was going to. So it just must not have existed until I hit it. Like, that is so fundamentally, egregiously retarded. I cannot believe that that's actually the basis for why he believed that there was inherent uncertainty. It's a physical interaction between a gamma ray and an electron where it transfers energy to the electron and changes its path. Oh my God.
Get a rope. Get a rope.
Nice. All right. We got one more from the homie on the cat thing.
Real quick, before we go on with this other one from the homie, let's just say everyone go subscribe to It's BS.
Yeah.
If you like his content, because I know I do, and he makes a lot of great videos like that one we just watched and the one we're about to watch.
Yep. And also follow him on Twitter where he does fantastic work.
He's the best Twitter follow ever.
His Twitter handle is at
Great
It's BS _YouTube. Put the link in the chat for the boys.
Nice.
Then hit like buttons and do all that stuff. All right.
All right, let's.
So are you ready? Are you lads ready?
I am.
Let's start right here.
What is quantum computing? Yeah. So it's a proposal for a new type of computation, or let's say a new way to harness nature to do computation that is based on the principles of quantum mechanics.
The problem with that statement is that quantum mechanics does not describe nature. It can't harness the power of nature because it is a pseudoscience. Now, most people tune out right here because they think that quantum mechanics is our best working theory. But what most people misunderstand is that we're actually using Schrodinger's wave mechanics and not quantum mechanics. And this is not my theory. Wave mechanics and quantum mechanics both use the same math, but quantum mechanics applies the complete opposite meaning to the Schrodinger wave equation. Okay, let me show you what I'm talking about. In 1933, Erwin Schrodinger won a Nobel Prize for the discovery of a new productive form of atomic theory. His Nobel lecture was on wave mechanics and not quantum mechanics. Now, Werner Heisenberg also gave a Nobel Prize speech the day prior because his prize was delayed by 1 year. He was one of the founders of quantum mechanics, and that is exactly what his speech was about. Now, back to wave mechanics. Schrodinger described quantum mechanics as point mechanics, or point particle mechanics, which differentiates it from his wave mechanics. This idea just doesn't seem to get taught. Instead, wave mechanics is just the equation used in quantum physics. But really, wave mechanics is more than that. It's the actual competitor to quantum mechanics. The point particles of quantum mechanics collide in a completely different manner than when waves collide with each other. This type of interference pattern is created during wave collisions. So how can a wave-based physics and a point-based physics both be using a wave equation to describe nature? Okay, let's continue.
Okay, so what does quantum mechanics say about the world? The physicists, I think, over the generations, convinced people that that is an unbelievably complicated question and, just give up on trying to understand it.
A quick suggestion. Don't fall for this line by physicists saying that you're not going to be able to understand this stuff. Modern physics has made some very fundamental errors that adds to this idea of complexity and confusion. You don't have to believe me about this. You can test this out yourself.
I can let you in, not being a physicist, I can let you in on a secret, which is that it becomes a lot simpler if you do what we do in quantum information theory and sort of take the physics out of it.
You have to be careful with this because now you're taking a leap of faith and believing that the physicists are correct.
So the way that we think about quantum mechanics is sort of as a generalization of the rules of probability themselves.
So at this point, computer scientists would be jumping straight into the math. Instead, let's take a look at a common fairy tale that is told about quantum physics.
Molecules, atoms and molecules, they operate using the laws of quantum mechanics, or by the laws of quantum mechanics. Us here have different sets of fundamental laws that allows us to kind of predict what we do, classical mechanics. And quantum mechanics and classical mechanics are very different.
Okay, so let's debunk this idea that we need a specialized physics for the small worlds of molecules and atoms. We are going to look at Schrodinger's 4 lectures on wave mechanics from March 1928. He discusses this topic in the first lecture. Ordinary mechanics is only an approximation which no longer holds for very small systems. But Schrodinger's description is different than what quantum mechanics says. Ordinary mechanics, or classical mechanics, treats many things as projectile paths and mass points. This would be just like the idea of calculating a baseball flying through the air. And specifically, when you are describing light in terms of a ray, which is like a straight line path, it becomes just an approximation and can work in the world of the big. But when things get really small, like within the atom, treating light with the ray method is of no use. So wave mechanics is what is necessary in the world of molecules and atoms. But here's the kicker. Wave mechanics still uses classical wave physics. Basically, he is saying that the requirement for the atomic world is to use waves. And the quantum theory guys were using mass points like electrons and photons, and paths like electrons orbiting around a nucleus. So the big difference here is how Schrodinger treated the electron. Quantum theory treated the electron as a particle moving along a path, and Schrodinger treated the electron as vibrational waves of a field of negative charge. And by waving this electron medium, he is able to explain what we observe experimentally about atoms, and it's consistent with the classical electrodynamics of Maxwell. So just think about what Schrodinger did here. He just made quantum theory obsolete because his wave equation describes the atomic experiments. And he does this using classical physics. Okay, so here is a question for you. If Schrodinger reunified physics with the wave idea and the wave equation to prove all of the observables of the atom, wouldn't you think that Schrodinger's wave mechanics would deserve its own section on Wikipedia? I mean, at least get its own section on Wikipedia? Or maybe see some of Schrodinger's ideas in the mainstream physics videos. Instead, it seems to just get shuffled under quantum mechanics and quantum physics, which still keeps physics separated. And many times you might hear that Schrodinger's cat is a thought experiment that helps explain the Copenhagen interpretation of quantum mechanics. This is Schrodinger's 1935 paper where the actual Schrodinger's cat paradox comes from. Now, as I just showed you, Schrodinger has already explained away the need for any of these quantum mechanics or quantum theory type of explanations in physics. But they still persist, and Schrodinger is making fun of how quantum mechanics is using his wave mechanics equation. So using quantum mechanics, one can even set up quite ridiculous cases. And Schrodinger's cat is just one of those cases that he was describing to help you understand why quantum mechanics is ridiculous. So maybe something was lost in translation, but it seems like ludicrous would have been a stronger translation of this German word. And it's crazy to think that the popularity of Schrodinger's cat, it's just one little paragraph in this paper. I'd like to continue on with the current state of quantum computing. But if you don't understand what separated quantum physics from classical physics, you might be thinking that it's just one person's word against another. So I need to quickly run through what made quantum physics a separated physics. The separation of quantum physics from classical physics really gained steam with the introduction of the Bohr atomic model. In 1913, Niels Bohr introduced his model of the atom, and his idea was that classical physics or classical electrodynamics was inadequate for describing the behavior of a system of atomic size. He based this idea on a previous atomic model that failed. And remember that Schrodinger's model of the atom uses classical or ordinary electrodynamics, which is the opposite of what Niels Bohr is saying. This is the first assumption that Niels makes that splits quantum physics from classical physics. It's the idea that the electron can orbit the nucleus but not radiate any energy. Since classical physics would not allow that to happen, he is going to file that assumption into this new physics called quantum physics. And these new quantum orbits are called stationary states. Now take this assumption of the stationary state and transition between these different stationary states. You get another feature of quantum physics that cannot be explained by classical physics. This is commonly known as the electron jumping between orbits, or a quantum leap. And this orbiting electron takes no time to jump through space. Let's look at this PhET simulation of the Bohr atomic model. The electron is orbiting in the non-radiating stationary state of quantum physics, because classical physics would not allow this kind of perpetual motion to take place. Now, when we turn on the light source of white light, it is going to send particles of light at this hydrogen atom. When this electron particle gets hit by a light particle, it will jump orbits just like it did right there. This electron jump or quantum leap is another example of why quantum physics split from classical physics. So how do we know that any of these atomic model ideas have any validity at all? You use math to describe the ideas, and those answers should be pretty close to what we experimentally observe. And the Bohr model of the atom did a pretty good job at doing this. Let me give you a real quick example of how we would experimentally observe atoms. I will use the line spectra of hydrogen as my example. So you would electrify this tube that has hydrogen gas, and it's almost like a fluorescent lamp. You use a spectrometer tool to view this gas, and it gives you these bright bands. Each atom has a unique set of these bands of color called line spectra. And these are the unique spectral lines for hydrogen. Now, the math for the atomic model should properly predict each of these bands of color, and maybe even the brightness or intensity of the color. Also, how they are affected by strong magnetic or electric fields. So the Bohr model got some of this stuff right, but he had to use those non-classical assumptions that we now call quantum physics. Now, going back to Schrodinger's wave mechanics, his wave-based math was in complete agreement with these experiments. But there is a very major difference here. Schrodinger explained the atom without using the quantum conditions of stationary states or jumping electrons. In fact, he got rid of the electron particle itself and the orbital path that went around the nucleus. So now do you see how Erwin Schrodinger reunified physics by getting rid of the need of those quantum physics assumptions?
Look at that big old dome.
Why
Dude's got
doesn't
a fat
wave
brain in
mechanics
that melon.
get the publicity? And why do you always see Schrodinger's work get combined with its competitor? So the last part of this story has to do with Werner Heisenberg and how we transition from quantum physics to quantum mechanics. And in 1926, Schrodinger writes this paper that shows that his wave mechanics and Heisenberg's matrix mechanics, or quantum mechanics, are getting the same answers. And remember that Schrodinger said that these quantum particles and their paths will not work in the world of the small. So how are they getting the same answers? And then we have to figure out the real difference between Schrodinger's wave mechanics and quantum mechanics.
Schrodinger hated what Max Born said. Einstein hated it. But never mind, Max Born was right. Max Born said it represents probabilities.
So why exactly was Max Born right and Schrodinger was wrong?
Schrodinger cat experiment was a way of Schrodinger to try to say how ridiculous the probability interpretation was. Of course, it's not ridiculous, it's right, and
in the next video, we will continue to understand why quantum mechanics is a pseudoscience, and we'll return to talking about the current state of quantum computing.
What's the next video?
Well, you want to watch it? It's a good one.
What is it?
I think we
I don't know
should.
if
This video is about how
About quantum computing and how it's a ruse.
I thought it was electron theory can't explain. Oh no, never mind. That's something different.
Yeah, yeah, it's in relation to like another part of it. This is a series, but they're not. This is like part 2 of what he was just talking about. So do you want to watch the quantum computing?
I think I've seen all these, but yeah, let's watch it.
how and why quantum computers are fake. This might sound like a conspiracy theory to you, but I am going to show where I got my information so you can evaluate it and come to your own conclusion. Here are a couple of concepts that you need to know so that you can understand what quantum computers are supposed to be. So this is how quantum computers and normal computers are the same. Quantum computers still use the same concept of zeros and ones, or on and off, and these are known as bits. Now the big difference for a quantum computer is something called quantum state superposition. Now this is where the concept of a quantum computer starts, and ironically, it is where the quantum computer ends. This is because quantum state superposition is not real. This does not exist. So now we have a quantum bit that can be a 1 or a 0, just like a classical bit, or it can be in this quantum state superposition. So what does that mean? On one side of the spectrum, you might get an answer that sounds like it's all possibilities between 0 and 1 at the same time. Or another illogical answer would be it's 0 and 1 at the same time. In other words, how can something be on and off at the same exact time? And on the other end of the spectrum, you have explanations such as it's like a coin flip, or it's a point on a sphere or a circle. Now these last two analogies make more sense to us because they're just describing analog processes, or classical physics and not quantum physics. So how do we know if quantum state superposition is real or not? And that is a big problem. By definition, you can never observe this state of magical on and off at the same time. So you have to believe it's real. A very famous example of this problem is called Schrodinger's cat. Now realize that Erwin Schrodinger himself wrote about the cat being dead and alive at the same time to show the silliness of quantum mechanics. In mainstream science, it seems like they've taken his idea, turned it around, and use it as a teaching tool for quantum mechanics. So why would so many smart people believe in something that seems so silly? I'm not sure I can answer that, but I think it has to do with the belief that quantum mechanics has been proven time and time again to work. Now, my statement is that this is the first device we've ever tried to build based on the principles of quantum mechanics. Now, I realize that almost everyone's going to disagree with that. And I don't blame them, because it takes more knowledge of what is wrong with quantum mechanics in order to better understand my statement. For now, think of a device that has ever tried to implement quantum state superposition before. So at this point, everything I've said can be verified by watching popular quantum computer videos on YouTube. Just realize that they believe that quantum state superposition exists. Those videos will also help explain why we're even trying to build quantum computers in the first place. One thing you'll hear about that is related to quantum computing is quantum entanglement. Now, in this video, I'm not going to go into detail what quantum entanglement is because it requires quantum state superposition to be real. If quantum state superposition is not real, then neither is quantum entanglement. And finally, you might hear that we've already achieved quantum state superposition and quantum entanglement using photon particles. The big problem with photon particles is that there is no definition that exists for a single photon particle. So if this sentence right here doesn't make any sense to you, then what I can do is refer you to another video I did that will go into more detail and explain what is wrong with the photon particle. This is the video that is on my channel that goes into more detail about why the photon particle is incorrect. But this is not a prerequisite for understanding the rest of this video. Okay, so now I will demonstrate how a classical computer works and how a quantum computer is supposed to work. Here we have a basic diagram of how your computer performs logic. We have 2 bits of information that you can think of as being stored in the computer memory, or RAM. These are connected by wires that go to a logic gate. You can think of this gate as being a processor, or CPU. This is the output wire from the processor that in this example is just connected to an LED light. This computer has 4 possible states that this processor can take as inputs. The logic is based on this wire being turned on and this wire being turned on at the same time. When this occurs, it will turn on the output wire that lights up the LED. So your computer has to send in each one of these states one at a time. So let's try this out. First we have the 00 state, and then we're going to have the 01 state, and you can see that this wire became electrified. Now let's have the 10 state, and then let's send in the last state, or the 4th state, 11. Both wires are electrified. The processor took this input and then turned on the output to make the LED light up. That's how a normal classical computer works, and anybody can understand that. This is called digital logic. So now let me try to describe what I call quantum illogic. Instead of using 4 separate steps to input these states into the logic gate, a quantum computer will set these bits in a quantum state superposition. Now what that means is they can be 0 and 1 at the same time. And if they are 0 and 1 at the same time, then you can send that quantum state superposition into the input of a quantum gate. This allows you to skip the 4 separate steps and just do it all at once. This is referred to as quantum parallelism, or the parallel processing advantage that you get over classical computing. So the first problem with this is, how would you ever know that these are actually in a quantum state superposition where they're both 0 and 1 at the same time? Because by definition,
right,
if you look at these bits or observe them or interact with them, what happens is that superposition collapses down to a classical bit state. In other words, you'll always see a 0 or a 1. You'll never see 0 and 1 at the same time, by definition. Again, the quantum computer has the advantage of sending all 4 states in a single step instead of sending each state one at a time. This is where quantum computing breaks down because quantum state superpositions do not exist. But let's keep following along. So you can apply quantum logic gates to this superposition of states, and somehow it doesn't disturb or observe the system. And then when you decide to take a measurement, the output of the gate is just one of the possible states. You don't ever have access to this superposition of all states. Now, if that's confusing to you, don't worry, because quantum computing is illogical and wrong. So then, what are these quantum computers that are available for people to use? There's a simple answer to this. They are analog random number generators. So this is the article that was written up by Google when they claimed their quantum computer was supreme to any classical computer. But what did it do? What Google did to demonstrate quantum supremacy was take a large sampling of random numbers from their quantum qubit circuits. And that's it. So where is the quantum computer speedup over classical computers coming from? I talked a little bit about parallelism, but that message seems to be going away since it's obviously not working. So it seems as if the parallelism is now changed to quantum speedups come from interference. So for a beginner overview video, I can't really get into what this actually means, but realize that it still requires quantum state superposition to be a real thing. Okay, so let's move on to more about why quantum state superposition is not real. Where did this idea of a quantum state even come from? We have to go back to old quantum theory where Niels Bohr was describing how an atom works. So this is the model of an atom that I think most people are familiar with. This refers to an electron orbiting a nucleus, but somehow not radiating light continuously and falling into the nucleus of the atom itself. This next one I think is more familiar to everyone. It's the idea that an electron makes a quantum leap, or this mysterious jump between orbits, and it jumps instantly through time and space. Niels Bohr justified these ideas basically just by saying, since stable atoms exist and we can't explain this using classical physics, well then quantum weirdness must exist. And then he spent the next decade or so trying to figure out how to bridge that gap between the quantum weirdness and everyday life classical physics. In 1925, Erwin Schrodinger created his famous wave equation that began to explain all of this quantum weirdness just by using classical physics equations. So his equation was making the right predictions for the atom, and again, it was doing this without bringing in any of the quantum ideas or probabilities. You have to realize that Schrodinger's equation is wave mechanics and not quantum mechanics. Wave mechanics is the opposite of quantum mechanics because this is dealing with waves and quantum is dealing with particles. This is Schrodinger's 1926 paper where his wave equation comes from. He says that the point of view taken here is rather that material points consist of or are nothing but wave systems. Right here he's talking about how this new theory can explain the electron quantum leaps, which up to date have been wholly mysterious. You can see that he's not using the idea of an electron as a concentrated point, but rather it's spread out through the whole space of the atom. So the Schrodinger equation is like the holy grail of quantum mechanics, but the solutions to the Schrodinger equation are not quantum. They are wave mechanics. They are solutions that are based on classical physics math. So then where does quantum mechanics enter the picture? Right here. Max Born hijacked Schrodinger's equation and gave it his own meaning. In this paper, Max Born uses the Schrodinger form of quantum mechanics, whatever that is, and attempts to apply his own interpretation based on an idea that he got from Einstein that determines the probability of a photon. So remember the quantum weirdness of stationary states and of the electron quantum leap. Max Born admits here that the Schrodinger equation does justice to these problems in the simplest way, again, in a classical physics manner. So what does Schrodinger think about Max Born's idea of probabilities applied to Schrodinger's own equation? In this paper, written by Schrodinger, he talks about Max Born's idea of probability and probability amplitudes, and then he gives his own comment right here, saying, I am averse to this conception. Averse meaning having a strong dislike or opposition to. And instead of a translation to English, we have the original German phrase right here. And so what does all of this mean? So we have one man's opinion on how he can force the idea of quantum particles into a classical wave equation. He does this by ignoring the answers that Schrodinger's wave equation gives and tries to convince us to focus on one answer that tells us the probability of finding a particle. Now I'm going to do a visual demo to show you how this idea creates quantum state superposition. But right now I want to show you another Max Born paper. It's just the preliminary version of the one I just showed you. I'm trying to point out how quantum computers and quantum mechanics both depend on this man's opinion. So after solving the collision problem with the Schrodinger equation, Max Born states right here, if one translates this result into terms of particles, only one interpretation is possible. This is the wave function, gives the probability for the electron. And this is where quantum mechanics begins. The opinion that Schrodinger's wave function gives the probability of the location for a quantum particle. This is called the Born rule, and there's no scientific proof that it's true. And just a side note, you see this asterisk? He had to correct himself and say it's the square of the wave function that provides the probability. And one last note, Max Born wants to give another opinion and let you know that he himself is inclined to give up determinism in the world of atoms. And what he's saying here is that when you choose to use probability and statistical math, that you will not be able to figure out exact locations for things in the world of atoms. Okay, so let's do a visual demonstration of quantum state superposition and tie together all of this talking. So here we have a PhET simulation of waves. Schrodinger's equation describes wave systems, so I'm going to send a single pulse down the line and then a second one. I'm going to pause it right here and explain. I have a reference line set up here so you can see the height or the amplitude of these waves, and then I can step them together and show you the constructive interference that occurs when two waves hit each other. At this point in time, we have a superposition of waves, and you can just think of this as waves of water. As we keep moving forward in time, the waves will go through each other and go back to their normal amplitude or normal height. Since Schrodinger's equation is designed to describe wave systems, you can see how naturally wave superposition is built right into this equation. Now, let's unnaturally force the idea of an electron particle into this equation. Now let's make this an electron and this an electron, and you can think of it as billiard balls. Let's step them closer together. And at this point, how are you going to describe these objects coming together as one? This is where you have to get creative and make something up like quantum state superposition. How can these billiard balls or electrons occupy the same space and time, pass through each other, and keep moving? And here's the answer. If you're going to translate that in terms of particles, it's obvious. There's one interpretation possible, and that is the probability for the location of the electron. So hopefully you can see that the Born rule of forcing particles into a wave equation is what creates the idea of quantum state superposition. In other words, a particle can be two different things at the same exact space and time. And the qubit of the quantum computer is based on this belief. Okay, that is it, and thanks for listening.
Thanks again. Shout out yet again. It's BS. If you like that video and the other videos that we watched of his, definitely go check him out on YouTube. His YouTube videos are great, and he's also fantastic to follow on Twitter. Or X, I mean. So yeah, good videos, Alan. Great choices, man. Some great coverage there.
Thank you, sir.
Anyone have any thoughts, questions? Anyone want to bring anything up? Wow, y'all quiet.
Fantastic.
I guess we're good with it.
Yep.
What's his handle on Twitter?
It's at itsbs_. I'll send it to you in DM.
_ YouTube.
Okay, thank
Yeah, let me make sure I actually just pull up. Will you drop it in the or you already dropped it in chat earlier? Yeah, there it is. It's BS_YouTube. Definitely go follow him on there, and definitely go follow him at It's BS on YouTube. So yeah, thanks again everyone for listening in. I think that's pretty much gonna wrap it up then, unless anyone else has anything else they want to say or any other final thoughts or anything.
You
Yeah.
gonna tune it up?
Oh, dude.
Oh, yeah.
Absolutely, Stone.
Dude.
Thank you, sir. Thank you. Is it on your BitChute?
Yeah, do we have it available?
Oh, most definitely.
Yeah. Light propaganda.
Or you could pull it off my very own. I got my very own channels, and it's a pretty high-res version, but this is probably good enough for broadcast. As usual.
All right, boys, we're going to close out here. But before we do that, quick announcement. Tomorrow, Flat Earth Friday, episode 108. And then on the following Tuesday will be Battle of the Beams Part 2, where I will be following up with Dave McKeegan's recent video. If you guys haven't seen his recent video, we tried to clap back a little bit, made a couple corrections to some things that I stated inaccurately, but those are already corrected, and we got all the math for that. So we'll be presenting that on Tuesday. Stone, take us away.
Yeah. Particles of mass all round. Talking about light propagation. Something that just can't be found. Talking about light propagation. Acting just like waves too. Talking about light propagation. That's a lie, I thought you knew. Talking about light propagation. This is light propagation. How does it come from years away?
Talking about light propagation.
All that time reaching us today.
Talking about light propagation.
Gravity don't cause no deviation.
Talking about light propagation.
That's the deal with light propagation.
Talking about light propagation.
Light propagation,
Talking about
baby.
light propagation.
An isotropic plate of
Talking about
day.
light propagation.
Ether's here and it's here to stay.
Talking about light propagation.
Ain't no crazy postulation.
Talking about light propagation.
I'm just talking about light propagation.
Talking about light
There's light
propagation.
propagation.
Talking about light propagation.
C plus V going up and
Talking about light
down.
propagation.
Back and forth to your side of town.
Talking about light propagation.
Dang, Wing had a lot of nerve.
Talking about light propagation.
Zero motion, straight off.
Talking about light propagation.
There's light propagation.
Talking about light
There's light propagation, baby.
Talking about light propagation.
There's light propagation.
Talking about light
There's light propagation,
Talking about light
baby.
propagation.
Booyah.
Awesome. Thanks for closing us out, Stone.